Part of today is going to be a review of all kinds of different reactions we've talked about already that involve the production of aldehydes and ketones. I'll give you a couple of new ones, and I'll be honest, today we're not going to talk much about mechanism, at least for this first part when we're prepping aldehydes and ketones. These are really just going to be, for now, just kind of note card reactions that we have to know, and then once we get into some of the carboxylic acid derivative chemistry, will start to kind of fill in some of the mechanisms of these things. The very first part of this, we're going to be prepping these two functional groups, and I will say that aldehydes are far more synthetically useful in general than ketones. So we'll kind of try to emphasize those a little bit more. And then in the second part of this, in a semi-unrelated thing, we'll just see how Grignard reagents will react with aldehydes and ketones, and hopefully that will serve as kind of our easier look at how ketones and aldehydes do their additions, at least in a basic type mechanism, and then we'll build into an acidic type mechanism in the very near future. So one of the first things I did was, just because I'm so bad with my memory in these times, I just kind of wrote down some of the reactions that we've already talked about, and then I'll highlight a few of the note card reactions that would be really helpful to know for different synthetic reasons. So, different ways of prepping ketones and aldehydes. Number one is the oxidation, which we've talked about in the just last lecture video. Oxidation of alcohols. And we talked about all kinds of different reagents, and it was a pretty recent video, so I'm not going to go into this too much, other than just to remember the fact that you had a whole series of reactions that were kind of the local train, where we could take a primary alcohol and end with an aldehyde. And then we had, of course, the secondary alcohols that eventually became ketones. Another really useful reaction, which you'll want to review, is the hydrolysis of alkynes. And we, of course, talked about just straight up hydrolysis with H3O+ back in the day, but we also talked about various reactions where, let's say, like a terminal acetylene could be treated with a boron species and we could end up with an aldehyde. That terminal alkyne could be treated with like a mercury species to end up with the ketone. Other kind of, I don't know, not super important in this context, unless it's a really particular aromatic material you're looking for, are the Friedel-Crafts acylations. And keep in mind, those will produce that benzylic, right, ketone for anytime you need that, which we could then clip off with some sort of Wolff-Kishner or Clemmensen reduction if we needed to. And number 4, which I don't find very useful, is the oxidative cleavage reactions that we talked about. I guess probably the most useful one of those is ozonolysis in reductive conditions. So make sure that you're familiar with these, review them. If you don't know what I'm talking about, ask me about them. Now we're going to go through some kind of newish type note card reactions. As I said, aldehydes are probably the more useful synthetically here, so let's highlight some special reactions that'll get us to aldehydes. So there are going to be a whole host of reactions that involve a reagent that is usually abbreviated as dibol, or sometimes dibol H. And this is actually diisobutyl aluminum hydride. As you will probably remember from our talk of reductions, aluminum hydrides generally reduce, right? Well, in this particular case, we're going to be taking a host of different carboxylic acid derivatives, and we're going to be taking use of this reducing agent. The diisobutyls are there to just kind of lower the reactivity so that we aren't going to see the typical type products from these reductions, right? They're not going to go all the way to the end of the line. Diisobutyl aluminum hydride and a few others really are the same thing as an aluminum hydride species, where instead of putting 3 other hydrogens on there, And so we're going to put diisobutyl groups on here, and you can see that, or kind of probably what you'd expect, is that these things are going to occupy some steric space, and it's going to make it a little bit harder for this reagent to actually, straight up add a whole bunch of H's and reduce things just due to sterics. Usually in these reactions, there's just about every aluminum hydride species requires some sort of quench. I'm going to put H3O plus, technically it could be H2O and things like that. And there's a couple of different ways that this will be abbreviated. Probably the most common are like this. Right? And so we'll learn to recognize this thing. It's a really useful type of reductive reagent. One example of where we could use this is any kind of ester. Right? It turns out that we're going to undergo a nucleophilic substitution type reaction. Like I said, we'll see the mechanism of this at the beginning of next term. But the ultimate product here is going to be an aldehyde. And it turns out that this is not the only thing that this thing is useful for to get to an aldehyde. It turns out we could have just as easily used some sort of nitrile, and a similar thing is going to happen. We could have started with a nitrile, also ended up doing a partial reduction followed by hydrolysis, and this once again is something that we're going to be seeing in a mechanistic form in the very near future. Another really good no-card reaction that, I'll be honest, I often forget which one of these processes requires a dibol equivalent and which one requires this other kind of crazy looking aluminum hydride reagent. But it turns out that this kind of altered reactivity hydride, which I believe this reagent is called lithium aluminum triterbutoxyhydride. It turns out that this thing is very good at doing that kind of local train reduction of this other carboxylic acid derivative known as an acid halide. So that's a pretty useful reaction as well. And this thing right here, as we'll see in just a second, is really, really good at reacting with other nucleophiles. But before we do that, let's take a glance at a couple of the reactions that produce ketones. So this reagent is something that we've seen before. It's known as a Gilman reagent, and keep in mind that Gilman reagents usually do kind of a more attenuated reactivity pattern relative to the Grignards that we're going to be talking about in just a second. And so we saw this back when we were talking about aromatic synthesis. And so a Gilman reagent, at least in this particular case, what we would need is an R prime, right, with a cuprous lithium salt. And the idea is that this thing is going to undergo a nucleophilic substitution, and it's going to substitute one of the alkyl groups on there. A couple other reactions that produce ketones and pretty high yield. This one I don't see very often, but it is in your book and it can get you out of a bind here and there. And the reason it's not super useful is that we're going to come up with a much cleaner way of doing these things in the very near future. And that is to use two equivalents of some sort of organometallic reagent known as an alkyl lithium. And it turns out the two equivalents are required because the first equivalent, like many nucleophiles, they're also really good bases. It will actually remove that H and then pretty much force a substitution reaction to occur such that we end up with that same exact product. The very last reaction that I'll show you here, that's kind of a special one to get to a ketone, is going to involve a Grignard reagent. And then after we learn that as a no-card reaction, we're going to kind of expand our view and see how useful Grignards are. Another really useful way of introducing a new alkyl group in the form of a ketone is to think about one side of that ketone as having resulted from a nitrile group. We already saw the reduction of one of these with an equivalent of dibol. Dibol will, of course, turn this thing into an aldehyde if that's what you want as your R'. But if you want to do a ketone instead, one of the things that's very helpful is the use of this thing, which is called a Grignard reagent. These things are incredibly useful ways of creating carbon-carbon bonds, and we will go through and we'll show exactly how some of those carbon-carbon bonds are created in the case of ketones, but in this particular case, the ketone is actually a product of the addition. So definitely something that we should write down. I should also remember to tell you that most of these things require some sort of quench step. So you'll often see these occur in 2 steps, very similar to the hydride reductions. So the reason we're introducing Grignards here is that they are a great example of carbonyl additions. And as I mentioned at the top, carbonyl additions can happen in either base or acid, and these are really good examples of the reaction as it occurs in base. One of the reasons I like to start with base in a lot of my mechanisms is that it's a much easier procedure mechanistically, right? And the reason is that a Grignard reagent, right? Let's just take methyl Grignard. We write out the methyl Grignard like this, right? It's an organometallic compound, but I think that it's more helpful to think about it as an equivalent of a carbanion, right? Much like what we used to do with like sodium alkoxide and sodium alkoxides and things like that. You kind of see the sodium as, you know, really just stabilizing the anion, right? And it's similar here, but this has a little bit more covalent bond character, so it may be a little confusing when you look up mechanisms and stuff like that. I just like to imagine the second that I see this, that what I have is a really, really strong nucleophile. The thing is that these things are also incredibly strong bases, right? And so it's really, really important, and I'll even write it down in red here, is that when you suggest suggest a synthetic protocol involving these Grignards, that you must be sure that you don't have deprotonatable H's, right? So that's kind of a sillier way of saying you can't have acidic H's anywhere. These things are incredibly strong bases, much stronger than any kind of base used in Gen Chem. If we were actually in lab, one of the first things that we do in third term is that I'd go through the synthesis, and you might even see it in a video I think I recorded a few months ago. That will show us how we can actually make these in lab, and you'll notice during this video I'm really careful, right? Because you can really melt your face off with as strong as these things are. And so that's pretty important. There are different ways that we're going to talk about synthetically as this course goes on of being able to kind of mask some sort of group that has an H that can get ripped off by a Grignard and then removing it after we've done the Grignard reaction. But for now, let's just kind of introduce the way that we would synthesize something like this and then how it would be used in some sort of ketone or aldehyde type addition. So the first thing that we have to recognize is how the heck are we going to make this? Well, it turns out it's pretty simple to do this. What you do is you start off with whatever halogen of the moment happens to be present, and you're going to treat it with magnesium in THF. So I love this kind of protocol because think about what you're essentially doing here. Is you're taking an incredibly electrophilic species, right, that we can use as a substrate in SN2 reactions and things like that. And we're simply treating it with one thing in a very, very simple step, and suddenly it's an incredibly strong nucleophile. So in synthesis, it's really common that you have this kind of like switch that you can throw, right? And we saw it kind of in the case of like amines and nitro groups, right? You could oxidize an amine that's on an aromatic ring and switch it from being an activator to a deactivator. In our aromatic synthesis, same exact kind of thing is going to happen here. Is that we can now have the ability, now that we've introduced these Grignards, to take any kind of electrophile, alkyl halide electrophile, and turn it very quickly into kind of the nucleophile that's going to reach out and attack something else. So super simple to make these things. So let's take a look at how this reaction proceeds. And so, as I said, it's pretty important that we remember that this is essentially an equivalent of a carbanion. And so this thing is going to be incredibly nucleophilic. First thing we're going to always do is make sure that there's no H that can easily get pulled off. And take my word for it, there is none. And so what we see is that that nucleophile is strong enough to directly attack that carbon, right? And that's something that's common in a basic mechanism. We can just get away with having the nucleophile directly attack the carbon. If for some reason we did a mechanism, some other mechanism that involved an acid, we'd usually have to protonate that thing first in order to kind of sweeten the pot such that the nucleophile wants to attack. That is not something we have to worry about in the case of a Grignard. Plenty strong enough to attack any kind of electrophilic carbon. So as a result of that arrow push, we end up with a new carbon-carbon bond. And you'll notice that we have this alkoxide. And that's the reason that we always need this H3O plus around, is that it will eventually protonate this thing. We end up with an alcohol product with a new carbon-carbon bond, right? And so now when we look back and we see anywhere we see an alcohol or something that could have started as an alcohol, that gives us a clue that any single one of those bonds could have come from some sort of Grignard reaction, right? So a super, super duper helpful reaction here. If you're looking at a secondary alcohol, right, the alcohol that has two carbon sides here, two alkyl groups bonded to it, it's usually come from an aldehyde. And I would say that's a pretty likely situation synthetically. The less likely one is for that thing to react with a ketone. So let's take a look at that tertiary alcohol type reaction. So just like an aldehyde can react with Grignards, ketones can react with Grignards in a slightly more attenuated fashion. Usually the aldehyde's a little more reactive. But we could easily introduce whatever we wanted. Let's say that this time we have an ethyl magnesium bromide. Through the exact same mechanism that we see before, what we'll end up with is some sort of tertiary alcohol with the addition of a brand new carbon-carbon bond, right? And so thinking retrosynthetically, anytime I see an alcohol, one of the first things I do is I go through and think, okay, what kind of ketone would I have started as if I maybe introduced one of those three bonds in kind of the penultimate step? That's a little bit of carbonyl addition with a whole lot of note cards that I just kind of threw at you. Hopefully we can see how all these things come together in some really nice synthetic protocols.